This video is a revision video about resultant forces. Starts off with content for everybody and then it ends up with content that is higher tier only. To start off, we're going to talk about stationary objects. So the first example, I've got an object here represented by the circle, and we call these diagrams free body diagrams. So we've got an object here, we've got 100 newtons to the left, remembering force is a vector with magnitude and direction. We've got a force of 40 newtons to the right. So how do we calculate the resultant? We simply take the biggest number and take away the smallest number because they're in opposite directions. So 100 take away 40 equals 60 newtons, that's our magnitude. But because the force is bigger to the left, our force is going to be to the left, so 60 newtons to the left. And that object, because there's a resultant force of 60 newtons to the left, will start moving to the left. In this second example, we've got 100 newtons to the left and 100 newtons to the right. To calculate the resultant, they're in opposite directions, so we take them away. So 100 take away 100, which equals 0 newtons. So that object will not move, it will remain stationary, it will remain still, it will remain at rest. But what happens if the object is already moving? So we're now going to look at some objects, and these objects I've said are moving to the right. They're already moving to the right. And I've drawn a free body diagram, and we've got 500 newtons to the right, we've got 200 newtons to the left. To calculate the resultant, we do what we've just done. The biggest number, take away the smaller number because we're in opposite directions. So we've got 300 newtons to the right. And the object was moving to the right, so that object's going to get faster, so it's going to accelerate. It's going to speed up to the right hand side. Now let's have a look if the forces are the same in those opposite directions. We've got 200 take away 200, which equals 0 newtons. And the mistake people make is they're going to think, 0 newtons, it's going to stop moving. That's incorrect. Because the object was already moving, it's going to go at a constant speed, constant velocity. What happens if we've got a bigger force in the opposing the direction of movement? So this object's moving to the right, we've got 200 newtons to the right, but 500 newtons to the left. So this time we're going to do 500 take away 200, which equals 300 newtons, but this time to the left. The object was moving to the right, whereas our resultant force is to the left, so it's going to slow down, it's going to decelerate. So it's going to decelerate, slow down, or you could say this is negative acceleration. You could say it's negative acceleration. And that negative acceleration means it's changing velocity, but in the opposite direction to what it's moving in. So this is for higher tier only. How do we do resultant forces that at right angles? All the ones we've just done have all been in the same plane, they've all been linear. So how do we do ones that are at right angles? Well, here we've got some forces, some vectors at right angles. That bottom is 40 newtons, which is represented by 4 centimetres. So 1 centimetre equals 10 newtons. So how big is this force up here? So we've got 2.4 centimetres, times it by 10, which equals 24 newtons. So the object's starting here, the object's starting down here, so where's it going to end up? The easiest way to do this is to make a rectangle out of this. So opposite our centre line of 4 centimetres, we draw another line of 4 centimetres. I'm going to draw it dashed so you can see the difference. And then opposite our side of 2.4 centimetres, we're going to draw another side of 2.4 centimetres. Notice how I'm drawing it nice and accurately. This will become important in a second. So the object started here and it's being pushed upwards and then to the right, so it's going to end up here. Or we could have pushed it to the right and then upwards. Either way, we always end up at that same place. So we started here and we finished there. So we join it up with a line. And then we put an arrow on the end to represent the direction. So we've now got the direction of our force. We've got the direction part of the vector, but we need the magnitude. To get the magnitude, we measure the length of our resultant force. So remember to do it accurately. So here I've got 4.6 centimetres. And then using our scale, 1 centimetre being 10. So we've got 4.6 centimetres times it by 10, which equals 46 newtons. And that's the magnitude of our force, and that's our direction. They could give you a compass and ask what direction it is, and that would be north-east. Or it could ask it for degrees, of which you'd use a compass and you'd put it down in bearings. If your forces aren't at right angles, but they still are at an angle, like so, you still do the same method. You draw a rhombus or a parallelogram, draw the resultant force, measure it, and then use whatever scale you've been given. So how do you resolve forces? So if you're given one resultant force, like here, if you've been given one resultant force, how would you work out what forces lead to that? So the object started off here and it's ended up down here. What we do is, first of all, we measure it, the resultant force, to find out what the scale is. So this line is 5 centimetres long, which equals 500 newtons. So 5 centimetres equals 500 newtons. So we divide it by 5, 1 centimetre must equal 100 newtons. So that's our scale we're going to be working with. What we need to do now is we need to turn this picture into a right angle triangle. So I'm just going to draw a dashed line so you can see the difference, and I've deliberately extended it beyond. And now I'm going to draw a vertical line down from my starting position. I deliberately extended it beyond again, and I'm just going to draw a right angle to represent the right angle. And now I measure the lines. I only measure the lines, I do not measure the extensions. So here I've got 4.4 centimetres. 4.4 times by 100, because that's our scale, equals 440 newtons, and that's our horizontal. Now to do our vertical, we measure again. Again, I'm not measuring the extended bit, I'm just measuring up to here, and that is 2.5 centimetres, timesing it by 100, which equals 250 newtons, and that's the vertical component. So we can get one of these forces and convert it into the horizontal component and the vertical component. If we'd done our right angle triangle on the other side, we'd have got exactly the same answers. So you don't need to worry about which direction you draw your right angle triangles. Just to show this, so we had 2.5 centimetres there, so this side should also equal 2.5 centimetres, and it does. This side was 4.4 centimetres, so this side should also equal 4.4 centimetres, which it does. So don't worry about which side you're drawing your right angle triangle on. If you've got multiple forces in the same situation, in the same scenario, we need to isolate it into horizontal and vertical to start with. So for example, I've got two horizontal forces, only one vertical force, so I'm going to resolve the horizontal first. So 70 take away 50 because they're in opposite directions, which equals 20 newtons to the right. So I've shown that with an arrow to the right. I've now got 30 newtons downwards. So what I'm going to do now, I'm going to redraw that to scale. So 20 newtons to the right, I'm going to draw as 2 centimetres. So starting from there where I put the dot, so that is 20 newtons, and now I've got 30 newtons down, so I'm going to draw that 1 centimetre, 2 centimetres, 3 centimetres. And where did they end up? Well, I know it's going to end up down there somewhere, but I need to do it accurately. So I draw my rectangle that we did on the previous sheet. So it's going to end up there. So it's going from there to there. So I draw my line, join them up. Put the arrow on the end to represent which direction the force is acting. Measure the line. So I've got 3.7 centimetres. And if 22 centimetres is 20 newtons, and 3 centimetres is 30 newtons, 3.7 centimetres must equal 37 newtons. So I've resolved this big picture up here. I've resolved the horizontal component first, then I've redrawn it to scale, and then I've done what we did on the previous page. And the last part of resultant forces, the most difficult bit, it's for equilibrium situations. If we're in equilibrium, the object is not moving. So here we've got a slope and it's been drawn at 45 degrees. They could do it at any degree. We've got our weight down of 70 newtons, and we've got the normal, which is at 90 degrees. We've got 90 degrees to the slope, and that's drawn not to scale. It won't be drawn to scale because to get the normal, which is the vertical component, you need to do a scale drawing. So first of all, what you draw is a parallel line to the slope from the bottom of the weight. So take my ruler, slide it down so it's parallel, and I'm going to draw my dashed line beyond. I then need to continue this normal line down until I reach my dashed line. So normal line down, and I extend it beyond so you can see where it crosses. I'm going to label it up as a right angle. I then measure the lengths of these sides to work out the scale of them. For example, my 70 newtons is 3 centimeters. So 3 centimeters equals 70 newtons. So how big is each centimetre? 70 divided by 3 is 23.3. So 1 centimetre equals 23.333 newtons. I'm going to measure my horizontal component first, which is from here to here. I'm not measuring the whole extension. And I've got 1.8 centimetres. So my horizontal, so I'm going to put H for horizontal. Actually, I'm just going to write the whole word. I've got 1.8 centimetres times by 23.333. So answer, so 1.8 times 23.33333, 41.9999, and I'm going to round that up to 42 newtons, only because it looks like there's a little bit of wiggle room. To get the vertical component, I measure it again. I've measured the vertical component from middle of the dot to here, and that is a distance of 2.7 centimetres. 2.7 centimetres, so my vertical I'm going to do over here. Vertical equals 2.7 times 23.333. So 2.7 times 23.33333 gives me 62.99999. 9999. And I'm going to round that up to 63. So I've got the vertical and horizontal components from this situation, from this equilibrium situation. If I wanted to, I could have done it a different way. I don't prefer this method because the first method you can just take the normal line downwards, but you can do it instead of drawing your line parallel to the slope below it, you can draw it through the centre of mass. So line your ruler up the slope, dashed line through the centre of mass. I'm extending it far deliberately, and then where the weight ends, I draw it at a right angle So I've now got another right angle triangle there. You can see that this triangle is the opposite of that triangle. So this length of 1.8 centimetres, this length up here would be 1.8 centimetres. This vertical component of 2.7 centimetres will be the same as this 2.7. So it doesn't matter which method you use, as long as there's a line parallel either at the bottom of the weight or going through the centre of mass, it doesn't matter, as long as you then turn it into a right angled triangle.